Welcome back, folks. We're talking about parabolas today, section 7.3 from our textbook. And parabolas are something you've been familiar with since your first algebra course. But what I think you'll find after we go through this lesson is that there's much more to the parabola than meets the eye. So I'm going to show you things about parabola today that you didn't know existed. And what I want you to do first is I want you to read everything in these top two gray boxes. Go ahead and pause the video, read your notes, and then I'm going to highlight some of the things in here that are important. No, seriously, pause the video and read the notes. Okay, great. Now that you've read the notes, let's go ahead and talk about the definition of a parabola. So the definition of parabola is it's a set of all points equidistant from a point and a line. So I highlighted the point and the line which we must be equidistant to. And remember, distances are measured as perpendicular distances. So the distance, well, excuse me, the perpendicular distance is to the line, but the distance to the point is just the distance to the point. So what distances are equal in this picture? Well, let's first look at this. That distance is congruent with that distance. Those two segments have the same length. Those two segments have the same length. And these two segments have the same length. So if you recall, we did a paper folding activity in class that after making some folds in the paper, we had a shape that resembled a parabola. And why is that true? So what we actually did in that activity was we made a fold like that. If we were taking this point here, which was one of our tick marks on the line we drew, and folding it over to what is now called our focal point or our focus, we created this fold here in red, and then that fold ends up being a tangent line to the parabola. And when you look at a bunch of those tangent folds, it kind of carves out the shape of a parabola. So that's what we saw in class with that paper folding activity. Now let's go ahead and talk in a little bit more detail about the different parts of a parabola. The standard equation of a parabola, a vertical parabola, is given as x minus h quantity squared equals 4p times y minus k. And the focal length is the absolute value of p. So in the picture, the focal length is this. It's the distance from the focus to the vertex of the parabola. So that distance right there is the focal length p, and I'll try and highlight that here. Focal length p. Remember that if p is greater than 0, the parabola opens up. If p is less than 0, the parabola opens down. Okay, next thing we'll talk about is a part of the parabola known as the latus rectum. And yes, that's seriously what it's called. Let me go ahead and show you what that looks like in the picture. The latus rectum is the segment connecting a segment whose endpoints are on the parabola and parallel to the directrix, but through the vertex, or excuse me, through the focus. So that segment right there is the latus rectum. I'll go ahead and underline the term in blue there so you know to reference the blue line that I just drew. How am I going to label these? Well, when you watch me do some of these notes, I'm going to label things as follows. I've got F here, which is my focus. I've got lowercase d, which is my directrix, and for this case, if the parabola opens up or opens down, the directrix, the equation is going to be y equals some number, because a horizontal line has an equation y equals a number. Then I have my vertex, which I'll try and label with the letter V. And then in this case, I have the left and right endpoints of the latus rectum. Keep in mind the following. The focal diameter, that's not necessarily a term that I'll use very often, but the focal diameter is 4 times p, and that's the length of the latus rectum. So from focus to one of the endpoints is half of that distance. So you could say the absolute value of 2 times p is the distance of that segment right there. Okay, let's now talk about forms of equations involving parabolas. Well, there's a couple that you already know. You've already seen this one. Okay, general form of a quadratic function. General form is the name that your textbook uses. It's y equals ax squared plus bx plus c. You've also seen standard form of a quadratic function. Some textbooks use the term graphing form. So I'm going to go ahead and write that in here, graphing form. And that's one where you can see h and k, the coordinates of the vertex. So these, you'll notice, are called functions because they're written as y equals some function of x. Then we got this guy over here that's called the standard of equation of a parabola. And I want you to look at that and see if you can figure out why it's not considered a function. Okay, there's a reason why this one's called an equation and not a function. And we're going to be working with both equations and functions throughout this lesson, so it's important for you to recognize the difference. If you don't know why that's not an equation, send me, or why this version is not a function, send me an email and I'll help you out. Okay, let's jump right in here and do some examples. Example 1. For each equation below, find the vertex, focus, directrix, and endpoints of the lattice rectum. Then, convert the equation to a function and graph it on your calculator. Sketch the parabola and label the important points. Okay, we are going to go ahead and get started by identifying this equation. And what I'm going to do for this first one is I'm going to rewrite it in the standard equation of a parabola. So if I write this as the standard equation of a parabola, it's going to be x minus 0, quantity squared, equals, I'm going to write here 4 times 1/2. I'll explain why I did that in just a second. And then y minus 0. Okay, so the reason why I wrote it in this form is I can now see that this is my h value, this is my k value, and that right there is my p value. Remember, the p value is called the focal length of the parabola. Okay, in this case, my p is greater than 0, so I know this parabola is going to open upwards. So how do I know that p is 1/2? Well, I need, stop jumping on me please, I need 4 times this number to equal 2, because originally I had a coefficient of 2 here. 4 times 1/2 equals 2, that's where I come up with that value. Alright, so we were asked to identify a couple of those features here. Let's go ahead and do that. My vertex, that's pretty easy, it's h comma k, so that's 0 comma 0. My focus, well remember the focus is in this case going to be above the vertex, and it's going to be above the vertex by p units because this focal length is p units, so I'm going to be p units above that. So I need to adjust my y coordinate, and I need to adjust it up by 1/2 of a unit. So my focus is going to be 0 comma 1/2. And remember that is absolute value of p units above the vertex. Okay. So how about the directrix now? Well, the directrix is the same distance away from the vertex as the focus is. It's just in the opposite direction. So now I have to go down 1/2 a unit below h comma k, and this one has to be written as an equation. This is y equals negative 1/2, and that's absolute value of p units below h comma k. Great. Now we need to talk about the endpoints of the lattice rectum. Well, let's go ahead and start by talking about this. The lattice rectum is the absolute value of 4p units long. and it's going to have a midpoint at the vertex. So with midpoint at the vertex, which is 0, 0. Okay, so the absolute value of 4 times p is going to be equal to 2. So half of that is 1. So I need to move 1 unit to the right of the vertex and 1 unit to the left of the vertex. So all of this information right here helps me figure out the following. The left endpoint is going to be at -1, 1/2. It's 1 unit to the left of the focus. And my right endpoint is going to be at 1, 1/2, which is 1 unit to the right of the focus. Okay, so that's all of the details about this parabola. The last thing I have to do is to sketch it. And for this first one, I'm going to go ahead and sketch it by hand, just to give you an example of how easy it is to sketch a parabola when you have all this information. So I've gone ahead and drawn XY axis here. I have XY axis, and I'm going to go ahead and mark my vertex. I'll label that with a V. Then I'm going to identify my focus. So if this is 1 unit, then my focus is at 0, 1/2. That's approximately right here. And I'll label that with an F. My directrix is at y equals -1/2. That is right about here. So I marked that point at -1/2 on the y-axis. That is just to identify the location of my directrix. And I'm going to go ahead and label that lowercase d for directrix, and that's the line y equals -1/2. Okay, so the last thing I have to do here is kind of identify the endpoints of the lattice rectum. That's going to be at -1, 1/2. That's right about there. And then +1, 1/2. Right there. And that's the left endpoint and the right endpoint. Now, notice, keep in mind that the parabola actually goes through those left and right endpoints and through the vertex. So that gives you a general indication of what the shape is going to look like. There. So that's a sketch of our parabola. We've identified all the important features. And again, what is this thing here we call the lattice rectum? Well, that is a segment that goes through the focus, has its endpoints on the parabola, and is parallel to the directrix. And our focal length, which was 1/2, is this distance right here. Okay, let's go ahead and move on to the next example. Folks, I spoke too soon. There's one last thing I have to do in this example. Don't forget to convert the equation to a function. So I need to make this x squared equals 2y look like y equals. And I simply do that by dividing both sides by 2. So y equals 1/2 x squared. And that is the equation of our parabola written as a function. All right, now we can move on to this next example. This one I'm going to go through a little quicker because we have a little more experience now. So this one's written in the standard equation as a standard equation of a parabola. This is my h value. This is the opposite of k because the standard form is y minus k. And then I have this value here, 2, which represents 4 times p. If 4p equals 2, that means that p equals 1/2. That's the same as in the last problem we had. That's a positive value, so this is also a parabola that will open upwards. So I'll go ahead and quickly rewrite this as a function. First thing I'm going to do is start with y equals, and then I have the quantity x minus 1 squared. Well, to get the y by itself, I'm going to have to divide by 2 or multiply both sides by 1/2. And then that would leave me with a y plus 3 on the right-hand side, so I better subtract 3 there. I've rewritten the equation as a function. Now it's time to identify the important features of this parabola. We have a vertex at 1, -3. We have a focus. Well, let's think. The focus has to be p units away from the vertex. In this case, since p is positive, the focus will be above the vertex. So I have to add 1/2 to the y coordinate. So that's 1, -5/2. Where on earth did I get -5/2 from? I did -3 plus 1/2, and that equals -5/2. The directrix will be a horizontal line that is p units below the vertex. That's going to be y equals -7/2. Where on earth did I get that? I did -3 minus 1/2, and that gives me -7/2. So next thing we have to talk about is the endpoints of the lattice rectum. The lattice rectum is 4 units long. Excuse me, that's incorrect. It's 2 units long. It's 4 times p, length of 4 times p. So it's 2 units long with midpoint at the vertex, at the focus of 1, -5/2. So since it's 2 units long, I have to move left 1 unit from this point for the left end point, and right 1 unit for the right end point. So the left end point will be at 0, -5/2, and the right end point will be at 2, -5/2. Notice that for the endpoints of this segment, I'm just moving left and right from the focus. Okay, now it's time to see that in a picture. You can graph this on your calculator, and you should be able to, if you needed to, graph that by hand as well. So we have our directrix at y equals -7/2. We have our focus at 1, -3. 1, -5/2. We have our vertex down here at 1, -3, and then you can see the left and right endpoints of that segment. Okay, I'm going to go ahead and work through example C now, and I'm going to go a little quicker even than I did on the last time. Let's talk about the function first. I know it has to be y equals. In order to get this y all by itself, the first thing I'm going to do is multiply both sides by -1/4. And then I'm going to subtract 3 from both sides. So there is the function form of this parabola. Now notice that I gave it to you in the graphing form, or what your textbook calls standard form. If I wanted it to be the general form of the quadratic, I would have to expand this squared binomial and combine like terms and do all that fun stuff. Okay, so back to the equation here. This is the opposite of h because, again, it's not written as x minus, so that's going to be the opposite of h. This is 4p, and this is going to be the opposite of k. So we do have a change here with this one. Let's take a look at 4. We have 4p equals -4. That tells me that p equals -1. So that gives us some new information, something we haven't seen in the previous couple examples. This parabola opens down because we have that p value as negative. From here we can go ahead and identify some of the important points of this parabola. Our vertex is going to be at -2, -3. Our focus is going to be p units away from the vertex. But remember, in this case, our focus will be below the vertex because the parabola opens down. So I have to be 1 unit below this. -2, -4. Might be worth noting here that this is p, absolute value of p units below the vertex. And my directrix is going to be above, the directrix will be above the vertex, so I'm going to have to shift 1 unit above this. That's going to be the line y equals -2. Again, that's p units above vertex. Why do we have the focus below and the vertex above in this case? Because our parabola opens down. Okay, so now let's talk about the endpoints of the lattice rectum. So for our lattice rectum in this problem, it has a length of 4p units, which is the absolute value of 4p, which is 4. So that means we have to go 2 units left and right of the focus. So 2 units left would be at -4, comma -4, and 2 units right would be at 0, comma -4. Notice the y-coordinate doesn't change. I have the same y-coordinate for my focus as my left and right endpoints. All that changes is the x-coordinate because we're moving left and right of the focus. Okay, that's all the important details about this parabola. Go ahead and take a look at the picture. You should be able to replicate that picture by hand if I asked you to. All you have to do is identify, not that, you have to identify the vertex, the focus, the directrix, and then the left and right endpoints. All right, folks, we're going to shut this down, and hopefully you can digest what we just did here, and then we'll start up a new video for the back side of the notes.